everybody and welcome back to another video. Now in this video I will be talking about a function of two inputs with three functions that it outputs. In this case, f of u comma v is equal to u times sine of v comma u times cosine of v comma v squared. And we will be finding the derivative of this function and evaluating it at 1 comma pi. Now you might be looking at this and saying, well, how do we do a derivative on this function? A derivative is defined as the change in one variable, or the change of the dependent, so this would be f, divided by the change in a independent variable, such as x. Now you might be saying, wait, there are three functions and there are two variables. How could we possibly encapsulate that in one scalar quantity? Now here's the thing, you can't. You cannot get a single number that will give you all of this information. Now you might be thinking, well, what about a vector? Now if we had a vector similar to this u sine v comma u cosine v comma v squared, that is a vector. However, we are taking the derivative with respect to this on both of them. So we are not just going to arbitrarily add more values this way to the vector. That would make no sense because we just have du over dv in its own spot just towards the end, which does not really make much sense. So what we can do is turn this into a matrix. So we could say that f prime of u comma v is equal to a matrix of the gradients of each of these functions with respect to u comma v. So this is our formula for our derivative. Now, what is a gradient, you may ask? The gradient is the derivative of each one of these functions with respect to these two variables. So what you would have is two partial derivatives. So gradient of a function for this value, u comma v, of uv is equal to a vector, which is df over du, where this is a partial derivative. I have another video on partial derivatives, if you could watch that one, or I will make another one. I will do a little explanation. This is just the derivative of f while holding v as a constant and only taking the derivative with respect to u. So let's just look at this first function for a quick second. So since sine of v has no u's on it, that is just a scalar. So we take the derivative of u, and this is just a constant multiplying that. Think of it as almost 5, you could say. I always say think of it as 5 when we have a constant term in there. So the partial derivative of this with respect to u just becomes sine of v. Now this is du over df, comma df over, or no, this is df over du, comma df over dv. So that is our gradient of the function, and we will be doing that 3 times and just listing them in order. So let's begin by taking the gradient of f1. So gradient of f1 is equal to the partial derivative of u sine of v with respect to u. So this is d of u sine v over du. And if you look, I just explained this one previously. However, this is just the only thing that has u in it, so this is a constant, so you can pull that out, and this just becomes du over du, that's just 1. So this is just equal to sine of v times 1, which is just sine of v. So this is that, comma, let's do this with respect to v now, of u sine of v. So now this u is just a constant multiplying by the sine of v, so this could come to the outside. So this becomes u times the derivative of sine of v with respect to v. The derivative of sine of a function with respect to that function is just going to be cosine of that. So this gradient would be sine of v, comma u cosine of v. And this is our gradient of function number 1. Now let's find our gradient of function number 2, which is u cosine of v. So I will be doing this one with a little bit less work on the board because we will begin to run out of space. So the gradient of f2 of u comma v is equal to the partial derivative of this with respect to u, which if you remember from the previous question, this is a constant, and then the u is just to the 1, so that just becomes 1, so this is just going to be cosine of v. That's our df over du. Now for our df over dv, this is a constant, so we could just look at this. The derivative of cosine of v with respect to v is just negative sine of v. So this becomes negative u sine of v. Now, let's look at our third function. So the gradient of f3 of u comma v is equal to the partial derivative of v squared with respect to u. I don't see a u in that term. That's just the derivative of 5 with respect to v, essentially. Or the derivative of 5 with respect to x. That's just 0. And it is 0, comma, the derivative of v squared with respect to v. There's no u in there, so it's just a simple first-order derivative, essentially. This just becomes 2v. So here are our 3 gradients of our functions. And now, let's write out our derivative. So f prime of u comma v is equal to this big matrix, which would be sine of v, u cosine v, then it would be cosine of u, then it would be negative u sine of v, then it would be 0 right here, and then 2v. So this is our f prime of u comma v. We have answered the first part of this question. Now let's evaluate this at 1 comma pi. So f prime of 1 comma pi is equal to the sine of v, when v is pi, is just going to be equal to 0, as the sine of 0 is just 0. So this is 0. The cosine of pi is negative 1. U is 1, so this is 1 times negative 1. So this right here is just negative 1. So let's put that right there. The cosine of, this is supposed to be v right here. It's kind of a little bit messed up. The cosine, yeah, this looks very much like a u over there, but that is in fact a v. The cosine of pi is just going to be negative 1 right here. And the negative, this is just negative 1 times 0, so this is just 0. And now we have this one, just has no input. This is just going to be 0 right here. And then 2v, v is just pi, so this is just 2 pi right here. So this is our derivative evaluated at 1 comma pi. Now you might be thinking, what on earth am I looking at? Why would I ever use this in mathematics? You could actually think of an application in research right now. So imagine this is just a table. So each way here, you have a different thing that you're looking at, and each way here, you have your dependent variables. So let's say you change the time of the experiment, then that is what happens right here while holding the other one constant. And let's say you change, what could you change in an experiment? Let's say you change the amount of food. Let's say that this is a research study. So delta F, and now, or let's say delta C, the change in calories. So then you would have a subsequent change in, let's say this is muscle growth. You would have, if you change the time, this is obviously not accurate. If you change the time that you're training, you'd have 0. That makes no sense. And if you change the amount you eat, you would have negative 1? That makes no sense. I clearly chose not the best application for this given matrix. However, this is just to help you see how you can apply this in real life. So anyway, I hope you all enjoyed this video, and thank you for watching.